And then if you have your hardened steel, okay, hardened steel, you can go between 150 to 300 meters per minute. And for aluminum, you guys know what I think about aluminum, okay? For aluminum, you can go 600 and up to infinity, okay? Whatever you want, okay? Right? So why this is the fact, right? Because when you head towards this direction, okay, the C value decrease, right? The C value decreases, okay? So the C value decreases means is what? Strain rate. Following this arrow is strain rate insensitive. So when it's insensitive, right? You can the range you can operate is much bigger. Okay, I'll write this out. So the strain rate sensitivity, okay, the strain rate sensitivity affects the range of cutting speed. Okay, it affects the range of cutting speed. So high strain rate sensitivity. Okay, high strain rate sensitivity material. Okay, my inks are all running out now. Okay, high strain rate sensitive material will tend to have, this is hopeless, will tend to have a more narrow, right, more narrow cutting speed range. Okay, so the more sensitive is strain rate, the range is much more what? Smaller, as you can see. Okay, so this is how strain rate sensitive will affect process parameter. And the last one, okay, is thermal softening index. Okay, so the thermal softening index is 1 minus theta ambient divided by theta melt minus theta ambient power of m. Right, you can remember this. So the thermal softening index m, okay, can be used, right? Can be used if increasing the cutting temperature by increasing the cutting speed right? So when you cut higher at higher speed, the temperature will be higher, will benefit. Okay, so the temperature in general will benefit in reducing the stresses, right? Reducing the stresses acting on the two. Okay, so if on the two and workpiece. Okay, So when M is less than 1, okay, you can cut at higher speed, okay, higher temperature, which is also an high cutting speed, will reduce the stresses. Okay, when M is greater than 1, okay, let's say you have a material where M is greater than 1, then forget it. Okay, so when M is greater than 1, okay, Mn is greater than 1, okay, so higher temperature were not reduced the stresses acting on the tool or workpiece. However, externally applied heat source might help, okay, the lowering of the stresses. Okay, so this is how, right, by looking at Johnson-Cook, by looking at Johnson-Cook constant, we can more or less plan our process parameter, cutter paths. Last week we do what rate angle to use. Okay, so the next thing we're going to do is we are going to look at into the mechanics. Okay, we're going to look at the mechanics of metal cutting using merchant's circle. Okay, so it's the first mechanics of cutting that we have seen. Okay, then this was developed in 1942, and we are still teaching it up to today. It's still valid. Okay, so merchant circle, as you can see, is a circle, but merchant circle has nothing to do with Mohs circle. I repeat again, merchant circle has nothing to do with Mohs circle. It's just a circle. Okay, so I'll try to draw a circle as best as I can. Okay, and at the center, right, that is my point O, and point O is the center of my circle. Okay, now I'm going to, there's going to be a lot of laboring. Okay, so draw your circle big. I highlight again, draw your circle big. Okay, so now we're going to next draw the tool. Okay, so this is the tool. Okay, that's our tool, and this is for positive rake. You can also draw for negative rate angle, you'll still work. Okay, so that's our tool. So we are going to draw a straight line from here to here, right? So the straight line is parallel to the rake face, okay? And this is known as our FC, okay? That is known as our FC. So FC, okay, FC over there is known as the force acting parallel. So sorry, is the force acting parallel to the rake face. Okay. So the units is in Newton per millimeter because we are dealing with 2D. Then you draw a 90 degrees line, right? This is known as your Fn. Okay. So sorry, not Fn, NC. Sorry, I do apologize. So this is known as our NC, and this is 90 degrees, by the way. Okay. So NC is force acting perpendicular to the rake face. Okay. And then the next one we're going to draw. Okay. This is a straight line. Okay. And the straight line passes, I know I cheated a bit, the center of the circle. And this is what we call R. Okay. R over here is our resultant cutting force. Okay. Then from here, we draw a horizontal line. Okay. And this is known as our FP. Right. And FP corresponds to our cutting force. Newton per millimeter. And then this is basically rules of the circle where we learn Mohs circle, we also have this, right? So this is our FQ. Okay. So FQ is usually known as our feed force. Newton per millimeter. Okay. And then we have our next one, next bunch of, so the next one we have our Fs. Okay. So Fs is known as our force. Okay, it's known as our force acting parallel to the shear plane Newton per millimeter, and Fs is oriented due to the pi. Okay, where pi is our shear angle and it's in degrees. Okay, and then the last one over here, this is known as our Ns. Again, that is 90 degrees again. So Ns is our force acting parallel to the, no, perpendicular. Hey. Perpendicular to the shear plane. Okay. And then we have an angle down here. This is known as our beta angle. And our beta angle is known as our friction angle. I mean, it's called a friction angle, but it does not mean coefficient of friction. Okay. So this is in degree. And then one more angle that we're going to have over here is our alpha. And we all know that alpha is known as our rake angle. Okay. Right. So this is the first mechanics, okay, of cutting. So what we are trying to achieve right? It's with this you can calculate stresses acting on the tool. You can calculate the stresses on the shear plane. Okay, so I'm not going to get rid of the circle. The circle is important to me.